Hi everyone. So today we'll be talking about power in DC circuits. Previously we looked at just voltages and currents, and today we'll be extending our analysis into power. I'll take you through the basic equations. We look at the concept of what we call load, and then we look at losses and efficiency. So you should be familiar with this already from high school. Electrical power is essentially the rate of change of energy per unit time. So if we look at that as a differential equation, we'll get dW dt, that is the rate at which work is done with time. And we could decompose this into dW dQ, which is the work done per unit charge, and dQ dt, which is the rate of change of charge. And as we all know from your earlier lessons, this is dW dQ is V and dQ dt is I. So that means the power PT is equal to VT IT. And here, when we represent them all in commons, we're talking about the instantaneous power is equal to the instantaneous voltage multiplied by the instantaneous current, which means if we have graphs of voltage, current, then with time, I would take this point and multiply it by this point, and I'll get some power P. This point multiplied by this point, I would get some other power. And if I continue to do that, multiplying these point by point, I will get PT, the instantaneous power. For DC circuits, of course, V and I are constants, which means P will also be a constant. So we get P is equal to VI. For DC circuits, we represent them with capitals, so you'll get P is equal to VI because these are all constant values for DC circuits. Now we know already that V is equal to IR, so if we substitute for V, we could get P is equal to IR by I, which gives us I squared R, or if I substitute for I will get V squared on R. And of course the units for power is the watt. The unit of power is the watt, and that is named after James Watt. There is another person that is of interest to us, and that is Telegun, and his theory states that the algebraic sum of the powers absorbed by all the elements in a circuit is zero at any instant of time t. And it sounds quite complicated, but actually it's just saying the power generated is equal to the power absorbed, which is the same in essence as the principle of conservation of energy. And talking about energy, we can calculate energy by looking at the integral of the power over time. Now remember, we had that graph before, and we said this is the PT here with time. And if we integrate P with time, that will give us the area under the curve, which is the energy or the work done. Since for DC circuits P is constant, then we just have to multiply it by T, since it's the area of a rectangle, and we get work done is equal to power multiplied by time. Good. So those are the basic equations. Now let's discuss a concept that is very important and often confused, and that is the concept of electrical load. You'll hear people talking about load a lot during the course of the program, and load means anything that you're trying to power, whatever is at the end of your end use for the energy, that is the load. And it could be lighting, heating, cooling, motors, electronics, whatever it is that is being powered by electricity, that is what your load is. And typically you have to send, well, not typically, in all cases you have to send the energy from a source through a pathway to the end point where the energy is used for the main purpose, and losses occur all along this pathway. So in a circuit diagram we could represent this as some source. This is a very simple representation, but it captures essentially what the problem is. We have some source here which is generating power, and at the end we have the load, which we represent by a resistor. And in this course we'll use either RL or R load to denote what the load is. And in between we have losses. So this could be losses in a transmission line, and that transmission line could be a line on a circuit board inside your phone, or it could be the lines going from one side of the country to the next. The concept is the same. In this case we have DC transmission. Across the country we have AC transmission, but for very long distances sometimes you also have DC transmission in larger countries. So this is the basis of what we're going to look at, and essentially what we want to do is we want to make sure that we lose as little power as possible. So all the power that we are transmitting, we want to get it to our load, and that is something we call efficiency. So imagine, if you want to think about it in a more everyday situation, imagine you're lifting a bag of groceries and you have to spend energy not only in lifting what is in the bag, the bread or whatever you have, you're also lifting the product packaging, the bag that holds everything, and also the weight of your own arm. So you have to expend energy to lift all of these things, even though the thing you really are interested in is the product itself, the bread. And it is the same thing with the power system. So in electric circuits, the power losses occur due to the circuit resistance. So it comes from the generating stations and it goes over the transmission lines, which are these thick conductors, or small conductors if it's in a phone or some electronic device, and all of these things have resistance. So to get to your house from the generator in Point Lisas or Pinal or Tobago, the power has to go through a whole network of conductors, and through all of these conductors you have current and you have resistance, and the power that is lost there is called it can be calculated using I squared R. So this is the loss power. So what we want to do is try to minimize this power. Now this brings us to the subject of efficiency, and efficiency is simply the output power over the input power. So a good efficiency will be when the output power is the input power, which will give us 100% efficiency. And sometimes you'll see efficiency denoted with this symbol neta. So if we have to look at a simple example here, what we're going to do is we want to find the efficiency, find the power dissipated in the circuit and the efficiency with which the power is delivered to the load. So if we want to find the power delivered in the circuit, the power coming from the source and the power going to the load, we need to find what are the currents in the circuit. So what is the current drawn by the source? What is the current supplied by the source? And we could use our simple circuit analysis. So we could reduce this to a single resistance of 8 ohms, and we have 10 volts. So the current is simply 10 over 8, which is 1.25 amps. Now we want to find what is the power delivered to the load. So we know P is equal to I squared R, which is the output power. So the current, which is 1.25 squared, multiplied by the resistance 3, and that gives us 4.6875 watts. The power from the source is 10 volts multiplied by I, P is equal to VI, which is 12.5 watts. So now we could find the efficiency P out on P in, which is 4.6875 over 12.5, which is 37.5% efficient. We could also find the power dissipated in the 5 ohm resistor, and that will be 5. So the power in the 5 ohm resistor, and that will be I squared, which is 1.25 squared multiplied by 5, and that gives us 7.8125 watts. So we have here 7.8125, and in the 3 ohm we have 4.6875, and for the 10 volt we have 12.5 watts. So what is the power supplied by the source? The power supplied is 12.5. The power dissipated is 7.8125 plus 4.6875, and if we add these two together we should get 12.5, and that would be, could you remember what theorem? Right, Telegan's theorem. So that was using currents to figure it out. We could also utilize voltages to figure it out, and here what we're doing is we're going to use P is equal to V squared on R. So what is the voltage across the 3 ohm resistor? We could use our voltage divider equation, and we could say that the voltage across here is 10 multiplied by 3 on 8, which gives us 3.75 volts. And then we have the power in the load, which is V squared on R load, which will be 3.75 squared over 3, which will give us the same 4.6875. And similarly you could do for the 5 ohm, and we will end up with the same efficiency. So to summarize, we just looked at the equations for voltage and for power and efficiency, and did some simple calculations with a circuit representing a source, some transmission network, and a load.